Hello, today I'll be talking about one of the more profound parts of linear regression, the geometry of it. So far, we've only been talking about it from the point of view of statistics, how it's about fitting a line of best fit. But there's a deeper connection. Let's dive in. First, let's recap some basic linear algebra. What's a dot product? A dot product is a way of measuring how similar two vectors are, how aligned they are. It tells us whether they're facing in the same direction, or whether they are facing in opposite directions. So basically, tells us a lower dot product means less similar, and a higher dot product means more similar. For instance, negative 50 of a dot product would imply that the vectors are not very similar. Well, 40, for instance, positive 40 implies that they are very similar. If the dot product is exactly zero, then the vectors are said to be orthogonal, which, if they are non-zero, this means that they are perpendicular, pointing in uh, directions with a 90-degree right angle in the middle. So how do we calculate this dot product then? Well, the dot product between A and B is defined as for each element or component in A and B corresponding to one another. For instance, the first component of each one, the second component, all the way to the n components. No matter how many components each one has, we take that and we multiply each one. And then for each multiplication between corresponding components, we sum them all up. So it's basically like a weighted sum again. And there's also an identity where the dot product is the magnitude of A, or basically the size of that vector A, times the magnitude of B, times the angle between the cosine, basically. If you look at this again, you can see that there's a very clear alignment between the dot product formula and the linear regression formula. They're exactly the same, just with different variables. The general dot product formula uses vectors A and B. But if we can compile all of our weights into one vector, for instance, we have W1 to be 2, W2 to be 3, etc., all compiled into one vector with the number of components in that vector being the number of weights or features, then we can also do that for the input vector x for each feature. Doing so, we can interpret this as exactly a dot product, so not just a weighted sum, but a dot product. Instead of fitting a line of best fit, if we let w be the weight vector and x be the input vector, linear regression is more than that. It's about measuring how similar two vectors are, more precisely, how similar the input vector is relative to the weight vector relative to the input vector. And the predictions that this model makes, for instance, 500 if you predict, or 200, they are not just a prediction, but also a measure of how similar the weight vector is to the input vector. So if you predict 50, even though it sounds very counterintuitive, it implies high similarity. And a prediction of negative 20 implies high dissimilarity, so they're not very similar. But here's the problem. Imagine if you're predicting house prices, right? Well, the prediction can easily be like, what, 200,000, 500,000? Because after all, the scale in which you're operating in is dependent on the task. In this case, the house prices, it's going to be very large because houses cost a lot. But does that necessarily imply that these two vectors are like very similar? Does that imply that they're overwhelmingly, extremely similar just because your prediction of the house price was like 500,000? Not necessarily. Because remember, the dot product, per the identity, also depends on the magnitude of these inputs and weights. If we go back to that formula, as you can see, the dot product can also be seen as the magnitude of A times the magnitude of B times cosine of the angle. And in seeing this, we can see that if A or B are like very large, for instance, they can easily make that overall dot product seem overwhelmingly large, even when that raw angle between them, cosine, uh, is not, the cosine similarity isn't that similar. So it can easily conflate that. The normalized version would be to use just raw cosine similarity, which is basically the dot product but without the magnitude terms. So if we just rearrange this, then cosine similarity equals the dot product divided by the magnitude of A times the magnitude of B. Here's where it gets really, really interesting. Suppose, for instance, you predict 0 for any particular task. Then the dot product is 0, right? And if the dot product is 0, if we go back to here, if the dot product is 0, so the magnitude of A times the magnitude of B times cosine is 0, and if we assume that A and B are both non-zero vectors, because if they were zero vectors, then the magnitude would be 0, right? But in this case, we assume they are non-zero because the data can't be like fully 0. Then that implies that for the dot product to be 0, the cosine similarity must be 0. And if the cosine similarity is 0, implies that the weight vector, W, is exactly perpendicular to x. So it doesn't seem like there's much to it right now, because so what? If the weight vector is perpendicular to the input vector, what insight does that bring? But this becomes especially useful when we encounter linear regression's classification counterpart, which is logistic regression. And we'll connect this to what we call a decision boundary. And we'll show how when this dot product, when this prediction is 0, when the raw value is 0, i.e. the weight vector is completely orthogonal or perpendicular to the input vector, we'll show that this acts as a sort of decision boundary, like at a state of maximum entropy, and how it's like at the border of two decisions.